Something about the universe feels slightly off, quietly, persistently off. It's not a loud contradiction or a dramatic paradox. It's subtler than that. Right now, as you read this, light that began its journey when time itself was just beginning has finally arrived. It has traveled across a distance so vast it resists intuition, about 46 billion light years, only to end its journey in your eyes. That alone should unsettle you, because it implies something deeper. What you are seeing is not just far away, it is ancient beyond comprehension. And it raises a question that refuses to go away. Does the universe have an edge? And if it does, what exactly are we looking at when we stare into the night sky? If questions like this pull you in, the kind that blur the line between physics and philosophy, then consider following the channel and subscribing. Because what comes next doesn't just expand your understanding of the universe, it challenges the very way you think about reality itself. At first glance, it seems straightforward. The universe is about 13.8 billion years old, so you might assume we can see 13.8 billion light years in every direction. Clean, logical, almost comforting. But that intuition collapses the moment you look closer. The true radius of the observable universe isn't 13.8 billion light years. It's about 46.5 billion. That number isn't a mistake. It's a consequence of something far stranger. Space itself has been stretching the entire time that light has been traveling toward us. Imagine a photon leaving a distant galaxy when the universe was still young, dense, compact, almost unimaginably small compared to today. That photon begins moving toward us at the speed of light, the fastest speed anything can travel. But while it's moving, the space between us and its origin isn't standing still. It's expanding, quietly, continuously, relentlessly. The photon moves forward, but the universe stretches beneath it like a cosmic conveyor belt. By the time that light finally reaches us, the galaxy it came from is no longer where it once was. It has been carried far away, much farther than a simple multiplication of time and speed would ever suggest. This is the observable universe, a sphere centered on us, not because we are special, but because light has had just enough time to reach us from within this boundary. Everything inside it is, in principle, visible. Everything beyond it is not hidden by distance alone, but by time. The light simply hasn't had enough time to arrive, and perhaps never will. But here's where it becomes even more unsettling. This boundary, the observable universe, is not a wall. There's no edge you could touch, no barrier you could cross. It's a limit defined by information. Light carries information, and nothing can travel faster than light. That means there is a maximum distance from which any signal could ever reach you. Beyond that distance, the universe doesn't cease to exist. It simply becomes permanently inaccessible. And this boundary isn't fixed. Every second, it expands. New light, emitted from slightly farther away, finally crosses into our cosmic horizon. Our view of the universe grows, slowly, like ripples spreading across a still lake. But even this growth has limits. There are regions so distant and receding so quickly due to cosmic expansion that their light will never reach us. Not now, not ever, no matter how long we wait. To understand this deeper, you have to move beyond the observable universe to something more fundamental, the particle horizon. This is the true boundary of what could, in principle, have affected us since the beginning of time. It marks the maximum distance from which light has had enough time to reach us since the Big Bang. Today, that distance aligns closely with the 46.5 billion light-year radius we observe, but conceptually it's more profound. It defines the edge of causal contact, the limit of everything that has ever been able to influence us. In the earliest moments of the universe, this horizon was unimaginably small. Only regions extremely close together could exchange light or information. But as time passed, the horizon expanded. More distant regions had enough time for their light to arrive. The universe, from our perspective, became larger, not because it physically grew in that moment, but because more of it became visible. There is, however, a hard boundary to what we can actually see directly, and it appears not as a line, but as a glow. This is the cosmic microwave background, the oldest light we can observe. It comes from a time about 380,000 years after the Big Bang, when the universe cooled enough for photons to travel freely. Before that, the universe was opaque, filled with a dense plasma that scattered light in every direction. There was no transparency, no clear signal, only a fog of energy. When that fog finally cleared, light was released in all directions. That light still surrounds us today, stretched and cooled by cosmic expansion into microwave wavelengths. It forms a kind of luminous shell around our observable universe, a snapshot of the universe in its infancy. When we look at it, we are not just seeing far away, we are seeing back in time to the moment the universe first became visible. And yet, even this ancient light is not the absolute beginning. Beyond it lies an earlier universe, hidden not by distance, but by physics itself. Signals like gravitational waves or neutrinos may one day reveal what lies beyond that glowing boundary, offering glimpses into times even closer to the origin of everything. So when you look up at the night sky, you are not seeing the universe as it is. You are seeing layers of history stacked across unimaginable distances. You are looking at a universe that is both expanding and slipping away, revealing more of itself while simultaneously hiding its deepest regions beyond unreachable horizons. And perhaps the most unsettling realization is this: the edge of the universe is not where things end. It's where our ability to know them does. But just when it seems like the boundaries of the universe are finally starting to make sense, another horizon emerges, one that is far more unforgiving. If the observable universe tells us what we can see now, and the particle horizon tells us what has ever been able to reach us, then the cosmic event horizon tells us something far more unsettling. What we will never be able to see, no matter how long we wait. This boundary lies much closer than you might expect, about 16.4 billion light-years away. And unlike the observable horizon, which slowly expands with time, this one behaves differently. It doesn't simply mark a delay in visibility, it marks a permanent loss. Beyond this distance, galaxies are receding so quickly due to the accelerated expansion of space that any light they emit today will never reach us. Not in a billion years, not in an infinite future. They are, in a very real sense, already gone. This creates a strange and almost paradoxical situation. Right now, you can look through a telescope and observe galaxies that are far beyond this 16.4 billion light-year boundary. You can detect their light, analyze their structure, even trace their history. But what you are seeing is not their present, it is their past. You are receiving photons that were emitted billions of years ago, when those galaxies were closer, when they had not yet crossed this invisible threshold. If you could somehow watch them continuously over unimaginable spans of time, you would notice something deeply unsettling begin to happen. At first, everything appears normal. Stars form, galaxies rotate, light travels. But slowly, almost imperceptibly, the galaxy begins to change. Not in itself, but in how it appears to you. Its light stretches, shifting toward the red end of the spectrum. This is redshift, caused by the expansion of space stretching the wavelength of every photon as it travels. The farther the galaxy, the stronger this effect becomes. Its colors fade into deeper reds, then into infrared, eventually slipping beyond the limits of what any optical instrument could detect. At the same time, the galaxy grows dimmer, not because it is losing energy internally, but because the photons reaching you are spread out over longer intervals. Time itself appears distorted. Events within the galaxy seem to slow down. A supernova that would normally flare and fade over weeks might, from your perspective, stretch over centuries. The galaxy begins to feel less like a dynamic system and more like a frozen image. And then, something even stranger happens. As the galaxy approaches the cosmic event horizon, this slowing becomes extreme. The flow of time, from your point of view, appears to grind almost to a halt. The galaxy seems to freeze at a single moment, its light endlessly redshifted, its signals increasingly delayed. The last photons it can ever send toward you struggle against the expansion of space, stretched thinner and thinner until they effectively vanish. Eventually, they stop arriving altogether. The galaxy doesn't explode or disappear dramatically, it simply fades, quietly, gradually, completely. This is the true meaning of the cosmic event horizon. It is not a wall in space, it is a boundary in time and causality. It divides the universe into regions that can still communicate with us and regions that are forever beyond reach. It is a one-way gate. Once a galaxy crosses it, no signal from its present or future can ever return. And yet, this boundary leads directly into one of the most counterintuitive ideas in modern physics, the notion that galaxies can move away from us faster than the speed of light without violating the fundamental laws of nature. At first, this sounds impossible. According to Einstein's theory of relativity, nothing can travel through space faster than light. This is one of the most firmly established principles in physics. And yet, when astronomers measure distant galaxies, they find something astonishing. Many of them are receding from us at speeds that exceed this limit, not just slightly, but significantly. So, what's going on? Is relativity wrong? The answer is subtle, but crucial. The key lies in understanding what is actually moving. Einstein's speed limit applies to objects traveling through space. It does not apply to space itself. And in cosmology, it is space, not galaxies, that is doing the expanding. Imagine placing two galaxies 1 billion light-years apart. The space between them expands at a certain rate, stretching the distance. Now imagine two galaxies 10 billion light-years apart. There is 10 times more space between them, and therefore 10 times more expansion occurring. The farther apart two galaxies are, the faster they appear to recede, not because they are moving through space at extreme speeds, but because the space between them is growing. At sufficiently large distances, this expansion becomes so significant that the effective recession speed exceeds the speed of light. But this doesn't break any physical laws, because nothing is locally outrunning light. Each galaxy, in its own local region of space, behaves normally. It's the large-scale structure of space-time that creates this illusion of superluminal motion. This leads to one of the strangest consequences in all of cosmology. A galaxy can be moving away from us faster than light, and yet we can still see it. That seems contradictory. If it's moving away so fast, how could its light ever reach us? The answer lies in the history of its motion. The light we detect today was emitted long ago, when the galaxy was closer and the expansion rate between us was lower. At that time, the photons were able to make progress toward us. As they traveled, they passed through regions of space where the expansion rate varied. In some regions, the expansion slowed relative to their motion, allowing them to continue advancing. Eventually, they reached us, even though the galaxy that emitted them is now receding at superluminal speeds. But here's the catch. If that same galaxy emits light today, those photons will never arrive. The expansion of space will carry them away faster than they can move toward us. The connection has been severed. We are seeing a ghost of the past, not a signal from the present. This realization forces a profound shift in how we think about motion, distance, and reality itself. The universe is not a static stage where objects move through empty space. It is a dynamic fabric, constantly stretching, reshaping the relationships between everything within it. Distance is not just a measure of separation, it is a measure of how space itself evolves over time. And in that evolving fabric, there exist boundaries not of matter, but of possibility. Regions we can see but never reach. Events we can observe but never influence. Galaxies whose histories unfold before us, even as their futures slip permanently beyond our grasp. The deeper you look, the clearer it becomes. The universe is not just vast. It is structured in a way that limits what can ever be known. And if the present already feels unsettling, if horizons limit what we can ever see, then the future of the universe is something else entirely. Because these boundaries are not static, they are evolving, tightening, and in some cases, quietly erasing the cosmos from view. Imagine standing under a night sky billions of years from now. Not millions, billions, even trillions. At first, the change would be subtle. The familiar galaxies beyond our local neighborhood would still be there, faint and red-shifted, but present. Then, slowly, one by one, they would begin to fade. Not because they are dying, but because the space between us and them is stretching faster and faster, driven by the mysterious force we call dark energy. This is the beginning of cosmic isolation. As time passes, more galaxies cross the cosmic event horizon. Each crossing is silent, invisible in the moment it happens. But its consequences are permanent. Light emitted after that crossing will never reach us. What remains visible is only the delayed echo of what once was. And as those last photons arrive, stretched and weakened, the galaxies begin to disappear. Not abruptly, but through a long, quiet fading. Eventually, even the grandest structures, the vast clusters and filaments that define the large-scale structure of the universe, will vanish from sight. Their light will be stretched beyond detection, slipping into wavelengths so long and energies so low that no conceivable instrument could ever capture them. They don't cease to exist, they simply exit our observable reality. What remains is a shrinking island of visibility. In the far future, the universe we can observe will contain only our local group of galaxies, a small gravitationally bound collection that includes the Milky Way, Andromeda, and a handful of smaller companions. Unlike distant galaxies, these systems are close enough and bound strongly enough by gravity to resist the pull of cosmic expansion. They will merge over time, forming a single, massive galaxy, an isolated structure adrift in an otherwise empty sky. To observers living in that era, the universe would look profoundly different. There would be no evidence of expansion, no distant galaxies racing away, no cosmic microwave background, as its radiation would have been stretched beyond detectability. The sky would be dark, static, and deceptively simple. From their perspective, it might appear as though the universe consists only of this one galaxy, surrounded by infinite emptiness. They would be wrong, but they would have no way of knowing it. This is what makes the idea of a cosmic prison so compelling and so disturbing. Not a prison of walls or barriers, but of information. Regions of the universe becoming permanently disconnected, not by distance alone, but by the fundamental limits imposed by space-time itself. Each gravitationally bound system becomes an isolated island, cut off from all others. Communication becomes impossible. Observation becomes incomplete. The universe fragments into countless disconnected domains, each unaware of the other's existence. And this is not speculation. It is the direct consequence of the accelerating expansion we already observe today. But even this picture of isolation and fading horizons is only part of the story. Because when we zoom out and examine the large-scale structure of the universe as it exists now, we discover that it is far from uniform. It is not a smooth distribution of galaxies scattered evenly through space. Instead, it resembles something far more intricate and far more uneven. The universe has structure, texture, contrast. Galaxies gather into vast filaments, forming a cosmic web that stretches across hundreds of millions of light years. At the intersections of these filaments lie clusters, dense regions packed with hundreds or thousands of galaxies bound together by gravity. But between these structures lie enormous regions of emptiness, voids. These cosmic voids are not completely empty, but they are strikingly underdense. Compared to the average density of the universe, they contain far fewer galaxies, less matter, and weaker gravitational influence. If you were to travel into one, the night sky would appear almost barren. Where we see thousands of galaxies, an observer inside a void might see only a handful of faint smudges at the edges of their vision. One of the most significant of these is the so-called KBC void, a vast region spanning roughly 2 billion light-years, within which our own galaxy appears to reside. Measurements suggest that this region contains about 20% less matter than the cosmic average. That might not sound dramatic, but on such enormous scales, it represents a profound deviation from what many cosmological models would predict. Even more extreme is the Boötes void, often referred to as the Great Nothing. Spanning hundreds of millions of light-years, it contains far fewer galaxies than expected, so few that its discovery initially seemed like an error. In a region where thousands of galaxies should exist, only a few dozen were found. It is one of the emptiest known regions in the observable universe. These voids are not anomalies in the sense of being rare exceptions. They are fundamental components of the cosmic web. They form naturally as gravity pulls matter into denser regions, leaving behind expanding pockets of low density. Over time, smaller voids merge into larger ones, creating vast expanses where matter is scarce and structure struggles to form. But their significance goes beyond structure alone. Void regions play an active role in how we interpret the universe, because they influence motion. Galaxies are not just carried apart by cosmic expansion, they also move under the influence of local gravitational forces. In dense regions, gravity pulls galaxies together, slowing their recession. In voids, where matter is sparse, there is less gravitational resistance. As a result, galaxies near or within voids can appear to move away faster than expected. This creates what astronomers call peculiar velocities, motions that deviate from the simple expansion of the universe. And these deviations matter, because when we measure the expansion rate of the universe, using distant supernovae or galaxy redshifts, we assume that most motion is due to expansion alone. But if we happen to live inside a large underdense region, like the KBC void, then our local measurements may be skewed. Galaxies around us may appear to recede slightly faster than they would in a perfectly uniform universe. This can lead to overestimating the expansion rate locally, a subtle bias with profound implications. It may even contribute to one of the most puzzling problems in modern cosmology, the discrepancy between different measurements of the universe's expansion rate. In this way, voids are not just empty spaces. They are dynamic regions that shape motion, influence observation, and challenge our assumptions about uniformity. They remind us that the universe is not a smooth, predictable system, but a complex structure with variations that matter. And when you connect this back to the idea of a cosmic prison, the picture becomes even more striking. Not only is the universe destined to fragment into isolated regions, but even now, its structure is uneven, its measurements uncertain, and its true nature partially hidden by where we happen to be located within it. We are not just limited by distance or time, we are limited by position. And that may be one of the most profound constraints of all. And yet, even after confronting isolation, fading horizons, and the unsettling role of cosmic voids, the universe still holds a deeper layer of structure, one that only becomes visible when you zoom out to the largest scales imaginable. What emerges is not randomness, but a vast, interconnected architecture known as the cosmic web. At first, this web is difficult to picture. It is not made of threads in the ordinary sense, nor is it something you could ever see with your eyes alone. But through large-scale surveys and simulations, a pattern becomes clear. Galaxies are not scattered evenly through space. Instead, they trace out enormous filaments, thin, elongated structures stretching across tens to hundreds of millions of light-years. These filaments act like highways of matter, channeling gas, dust, and galaxies toward dense intersections. At the points where multiple filaments meet, matter accumulates into clusters, gravitationally bound regions containing hundreds or even thousands of galaxies. These are the nodes of the cosmic web, the densest environments in the universe. Surrounding them are vast walls, sheet-like structures that connect filaments and clusters into even larger formations. And between all of this lie the voids we encountered earlier, immense, underdense regions that form the negative space of this cosmic pattern. Filaments, clusters, walls, voids. Together, they form a structure that resembles a three-dimensional network stretching across the observable universe. It is as if the cosmos itself has been woven into a delicate, intricate lattice, with matter tracing the threads and emptiness defining the gaps. But this raises an even deeper question. How did such a structure come into existence? The answer takes us back to the earliest moments of the universe, long before galaxies, stars, or even atoms had formed. In that primordial era, the universe was incredibly hot, dense, and nearly uniform, but not perfectly so. Tiny fluctuations existed in the distribution of energy and matter, arising from quantum processes during the universe's earliest expansion. These fluctuations were minuscule, variations of just 1 part in 100,000, but they were enough. Over time, gravity began to amplify these small differences. Regions that were slightly denser exerted a stronger gravitational pull, attracting more matter and becoming denser still. Regions that were slightly less dense lost matter, becoming emptier. This feedback process continued over billions of years, gradually sculpting the universe into the web-like structure we observe today. In this sense, the cosmic web is a fossil of quantum uncertainty, a macroscopic imprint of microscopic fluctuations stretched across cosmic time. What began as tiny irregularities in an almost uniform field evolved into a vast network of galaxies and voids, governed by the relentless pull of gravity. And yet, even with this framework in place, even with our best models and simulations, there are features of the universe that do not fit neatly into this picture. Subtle anomalies, deviations from expectation, signals that something might not be fully understood. One of the most intriguing of these is a region in the cosmic microwave background known as the cold spot. This is not a structure made of galaxies or matter, but a patch of the oldest light in the universe that appears slightly cooler than its surroundings. The difference is small, just a fraction of a degree, but statistically significant enough to draw attention. At first, this might not seem like much. After all, random fluctuations are expected in any large dataset, but the cold spot is unusually large and unusually pronounced. It stands out in a way that invites explanation. One hypothesis suggests that this anomaly could be caused by a massive supervoid, a region of extremely low density that photons from the cosmic microwave background pass through on their way to us. As these photons traveled through the void, the expansion of space could have stretched them further, lowering their energy and making them appear cooler when observed today. It's an elegant idea, but the evidence is inconclusive. While some large voids have been identified in the direction of the cold spot, they may not be sufficient to fully explain the effect. This leaves room for other possibilities. Another explanation is statistical. Given the sheer size of the observable universe, even rare fluctuations are bound to occur somewhere. The cold spot might simply be an unlikely, but not impossible, result of random variation. And then there is the most provocative possibility, that the anomaly points to new physics. Perhaps our understanding of the early universe is incomplete. Perhaps there are processes or structures we have not yet accounted for, remnants of phenomena that lie beyond our current models. The cold spot does not provide a definitive answer, but it serves as a reminder that even the oldest light in the universe may still carry unresolved mysteries. And this brings us to one of the most pressing tensions in modern cosmology, A discrepancy not in structure, but in measurement itself. A disagreement over something as fundamental as how fast the universe is expanding. This is known as the Hubble tension. There are two primary ways to measure the expansion rate of the universe, often expressed in kilometers per second per megaparsec. One method looks deep into the past, analyzing the cosmic microwave background, the same ancient radiation that revealed the cold spot. By studying its detailed patterns, scientists can infer the conditions of the early universe and extrapolate forward, arriving at an expansion rate of about 67 kilometers per second per megaparsec. The other method focuses on the more recent universe, using observations of distant supernovae and variable stars to measure how quickly galaxies are moving away from us today. This approach yields a higher value, around 73 kilometers per second per megaparsec. At first, this difference might seem minor, but in precision cosmology, it is significant. The discrepancy is larger than what can be explained by measurement errors alone. It persists across multiple independent observations, and it suggests that something, somewhere, is not fully understood. One possible explanation ties back to something we've already explored, our position within a cosmic void. If we happen to reside in a region with lower than average density, local galaxies may appear to recede faster than they would in a perfectly uniform universe. This could bias our measurements, leading to an overestimation of the local expansion rate. It's a compelling idea, especially given evidence for large-scale underdensities like the KBC void. But it may not be enough to fully resolve the tension. The alternative is more profound. It suggests that our cosmological model, the framework we use to describe the universe's composition and evolution, may be incomplete. Perhaps dark energy behaves differently than we assume. Perhaps there are additional components or interactions we have yet to discover. Or perhaps the laws governing the early universe differ subtly from those we observe today. In this sense, the Hubble tension is not just a technical problem, it is a signal, a crack in the foundation of our understanding. And like the cold spot, it reminds us that the universe, even at its largest scales, is not entirely settled. It is still, in some ways, unresolved. And when you place this alongside everything we've explored, the limits of observation, the inevitability of cosmic isolation, the vast emptiness of voids, and the intricate structure of the cosmic web, a pattern begins to emerge. The universe is not only vast and expanding, it is complex, uneven, and, in certain ways, still mysterious. We have mapped its structure, we have traced its history, but we have not yet fully decoded its rules. And just when it seems like every boundary has already been drawn, every horizon defined, every limit acknowledged, there is still one more layer to confront. Not a boundary of what we can see now, or what we will never see, but a final, ultimate limit. The maximum extent of everything we could ever possibly observe, even in principle, across the entire future of the universe. This is sometimes called the future visibility limit, and it lies at a distance of roughly 63 billion light-years. At first, this number feels like just another extension of what we've already encountered, larger than the observable universe, beyond the current particle horizon, another edge pushed slightly farther out. But its meaning is more precise and far more final. It represents the absolute boundary of all information that could ever reach us, even if we waited forever. Every photon that is ever going to arrive from the distant universe is already on its way, or it never will be. There is no hidden reserve of signals waiting beyond this limit. No matter how advanced our technology becomes, no matter how long our civilization endures, we will never receive information from beyond this boundary. It is not a temporary horizon. It is a permanent constraint written into the structure of space-time itself. In a sense, this is the true size of our knowable universe, not what exists, but what can ever be known. And yet, even within this limit, something irreversible is already happening. The universe is not simply expanding, it is diluting its own visibility. The signals that do reach us are being stretched, weakened, and transformed as they travel across the growing fabric of space. This brings us to one of the most subtle yet profound processes in cosmology: redshift. As light moves through an expanding universe, its wavelength is stretched along with space itself. A photon that began its journey as visible light may arrive as infrared, or microwave radiation, or something even longer in wavelength. Its energy decreases, its frequency drops. It becomes harder to detect, harder to distinguish from the background noise of the cosmos. At modest distances, this effect is measurable but manageable. We can correct for it, interpret it, reconstruct the original properties of distant galaxies. But as distance increases, as expansion accelerates, the effect becomes extreme. Light doesn't just redden, it fades into obscurity. Galaxies that were once bright and distinct begin to lose their definition. Their spectral signatures stretch beyond the range of our instruments. Their photons arrive less frequently, spread thin across time. What was once a clear signal becomes a whisper, then a trace, then nothing at all. This is not because the galaxies themselves are disappearing, it is because the information they carry is being erased by the expansion of space. Over vast timescales, this process leads to what some have called a kind of redshift graveyard, a regime where light still exists in principle, but is so stretched, so diluted, that it becomes effectively undetectable. Entire galaxies, entire regions of the universe slip into this graveyard, not destroyed, but rendered invisible in any practical sense. It is a quiet extinction of information, and it has consequences that reach far beyond observation. Because astronomy, at its core, depends on light. Everything we know about the universe, its structure, its history, its composition, comes from interpreting the signals that reach us. If those signals fade beyond detection, then knowledge itself becomes constrained. Future observers, living in that distant era we imagined earlier, would not just see fewer galaxies. They would lack the evidence needed to reconstruct the universe as we understand it today. The expansion of space, the existence of the cosmic microwave background, the large-scale structure of the cosmic web, all of it would be hidden behind the combined effects of horizon limits and redshift. They would inherit a universe stripped of its past. And this leads us to a conclusion that is as philosophical as it is scientific. The universe is larger than anything we will ever see. That much is clear. But more importantly, what we see is not the universe as it is the universe as it was. Every observation is a message delayed by time, shaped by distance, and filtered through the dynamics of space-time itself. We do not observe reality directly. We observe its history, and even that history is incomplete. There are regions forever beyond our reach, events that will never influence us, signals that will never arrive. There are structures we will never map, phenomena we will never detect, questions we may never even know to ask. The boundaries we've explored, the observable horizon, the particle horizon, the cosmic event horizon, and this final limit of future visibility are not just features of the universe. They are limits on knowledge. They define what can be known and what must remain unknown. In this sense, every observer exists within their own cosmic perspective, their own observable universe shaped by their position in space and time. Move to a different galaxy and the visible universe changes. Wait long enough and it shrinks. Look in a different direction and you sample a different slice of cosmic history. There is no single, complete view, only overlapping, partial ones. And this may be the most profound realization of all. The universe is not just physically vast, it is epistemologically constrained. It contains more than we can access, more than we can measure, more than we can ever fully comprehend. Our theories, as powerful as they are, operate within these limits. They describe a universe we can observe, but not necessarily the entirety of what exists. We are, in a very real sense, bounded observers, not by lack of intelligence or technology, but by the structure of reality itself. And yet, within those limits, we have managed to reconstruct a story that stretches from the earliest moments after the Big Bang to the distant future of cosmic isolation. We have identified the horizons that shape our view, the structures that define the universe, and the anomalies that challenge our understanding. We have learned that space can expand faster than light, that galaxies can disappear without vanishing, that emptiness itself can shape motion, that the universe can both reveal and conceal itself at the same time. And perhaps most importantly, we have learned that every answer leads to a deeper question, because beyond every horizon lies not just more universe, but the possibility that what we cannot see may be just as important as what we can.